Okay, the recording is running. So we'll start. Hello everyone, good evening. My name is Shaptur Shide. I am a PhD scholar at Electrical Engineering Department, IIT Bombay, and I work on electric machine design for my PhD. So this is one of the 3 doubt clearing classes for the NPTEL course Electrical Machines 1, and this is held on every Saturday, 7 to 8 p.m. So this is the 6th week. Okay, this is the last week for our transformer class, and from the next week you will see 7th week lectures are already released. There are DC machine, rotating electric machines have started. Only DC machine will be covered in this course. Okay, so this week you had mostly connections of transformers, several types of connection. One was Scott connection. Another thing was some kind of 3-phase to 6-phase kind of connections, and parallel operation of transformers. There was, after that, cooling of transformer. Yeah, that's all. So these 4 were the topics for this week. In the other doubt clearing class that was organized today at 4 p.m., their parallel operation of transformers have been covered. In this session now, I will be discussing mostly about Scott connection and 3-phase to 6-phase connection. These things I will discuss.
Today's session have a problem.
Sorry?
Today's session, which is from 4 p.m. to 5 p.m.,
Okay.
having some issues.
Technical issues were there.
Technical issues after 30 minutes.
Okay, so if you have some doubt from parallel operation, you can ask here also. I will try to discuss them.
Okay, sir.
All right. So can you guys just raise your hands? So let me know how many of you have watched some or all of the videos of week 6. Pushpraj and okay, Pushpraj, you can lower your hand. So what is Scott connection? Scott connection, we will start with Scott connection today. So Scott connection is nothing but 3-phase to 2-phase transformation. Now in a 3-phase, so you know that the 3 voltages of a 3-phase system are 120-degree phase shifted. We know the math. 360 by 3 is 120 phase shifted. Easy to understand. But the thing is, what about 2-phase? This calculation says that 2-phase should have 360 by 2, 180-degree shifted supplies. But is it true? This is not true for 2-phase. In 2-phase, the voltages are and the currents also are separated.
Double field revolving theory, sir. We apply for this.
Sorry?
Double field revolving theory we are using for this 2-phase.
Yeah. So they're 90-degree shifted. So balance 2-phase supply means 2 voltages which are equal in magnitude and 90-degree phase shifted. That is a 2-phase system. Now, do you guys have any doubt about Scott connection, or should I discuss it once in brief?
brief introduction needed. sir.
Okay. So in two phase, we have, in Scott connection, we have two transformers, two identical transformers. With tappings. Now, where those tappings are, we will see. With tappings, not changeable tappings, fixed tappings, but we need tappings. So, I will draw the two-phase transformer, the Scott connection transformer, how they look. So, this is the first transformer that I am drawing now. This is one winding of the first transformer, okay? Can anyone tell me what do these vertical lines signify? Or these lines when you draw transformers?
Coupling.
But if I draw two inductors and give dot, does it mean that they are not coupled? They have a proper meaning. This means core. There is some magnetic core present. Okay, so this is one. This secondary has N2 number of turns, right? And the other primary has a central tap. Okay, the other primary has a central tap. So how does it look? This is one half of the winding. This is another half of the winding, right? The central tap, and again there is a core and the second winding. Right? So this is the connection of a Scott connected transformer. Now this is N2, this is also N2 number of turns. Since they are connected in this fashion, so this, if this is dot, then this also must be dot, and this is dots, and let us say this is dot. Okay. Now, how are they connected to the three-phase supply? As we have said that this is a three-phase to two-phase conversion. So let us say this is connected to A. A means the three-phase supply is coming. This is the line A. And this is, let us say, connected to B. And this point is, I can draw it here also. Okay, let me just take it out somewhere here. This phase, this part is connected to C. So this is how the other part, the other end of the winding is connected. So this is how the Scott connection transformers, Scott connected transformers receives its supply, from the three-phase source. Yeah.
Sir, parallel line indicates core and dots indicates
Dots indicate the polarity.
polarity.
Yeah.
Okay, sir. Okay.
So here in this secondary, we have two loads connected. So it is a two-phase system. As understandable, there are two loads connected. This loads. Okay. N2, let us say this is N1 by 2, N1 by 2, as I told you that they are central tapped, N1 by 2, N1 by 2, right? Now the question is, what will be the number of turns here? As I told you that these are identical transformers. So this transformer unit has N1 by N2. This also has N1 by N2, but you cannot connect the whole N1 in the primary. We will see how. So what we can do is, say this is a point O, and let me write this as some V0. Okay. So what is this voltage? this voltage is VAB, right? Now, can you tell me this winding? I am giving a thing. Say I draw this polarity as plus minus. Can you tell me what is the voltage of this plus minus across this half winding of this primary? What is the voltage?
V1 by 2.
What is V1?
Supply line voltage.
Supply
VL
line
by two.
voltage, okay. But supply line voltage, there are three voltages, VAB, VBC, VCA. With respect
Okay,
to that, can you say?
Yes, okay. So we are giving VBC by 2.
This is VBC by 2.
Yes.
So this voltage is VBC by 2. Now we will apply KVL here and find out how much voltage is there across this V0 is how much we will find out. So the thing is, it will be VAB increasing minus V0 dropping again plus VBC by 2 equal to 0. So what we have out of this is V0 equals VAB plus VBC by 2. Can you not see my handwriting? Yes, come. There was some lag. Okay. Right, now we have to set our convention. So let us set our convention in this fashion that let us write, let us take our VAB line voltage as our reference. So VAB is V sine omega t. Then what will be VBC? What will be VBC?
Minus 120 degree. Yes, sin omega t minus 120.
Minus 120 degree. And VCA will be V sine
Plus 1.
omega t plus 120 degree. Okay. Now we can substitute. Okay, we will look at problems later once we understand these things. We'll substitute this and find out V0. So V0 is equal to V sine omega t plus V by 2 sine omega t minus 120 degree. Right? Can you help me doing this? We will quickly write sine omega t plus sine a cos b half sine omega t cos 120 minus half cos omega t sine 120. How much is cos 120? Minus half, right? No, cannot be minus half. Yeah. Cos omega at 120 should be minus half. Let me just check once. Yes, minus half. So we have sine omega t minus 1/4 sine omega t minus, this is root 3 by 2, root 3 by 4 cos omega t, right? So we have V1 minus 1 by 4 is 3 by 4 sine omega t minus root 3 by 4 cos omega t. So this is V0 in terms of sine omega t cos omega t. But the thing is, we have to write it as one, as something times sine or cos something we have to write. So to do that, what we can do is we can assume 3 by 4 as r, say, cos theta, and root 3 by 4 as r sine theta. Then what do we have? We have tan theta equals this by this. So root 3 by 4 times 4 by 3, that is 1 by root 3. So we have theta equals 30 degree. And from here we have r squared cos squared theta. So basically r squared equals 3 by 4 squared, 9 by 16 plus 3 by 16, 12 by 16, which is 3 by 4. So basically we have r equals root over 3 by 2. So from here what we can write is V equals, so V r sine omega t cos theta minus cos omega t sine theta, right? So sine omega t minus theta. If you have any doubt, ask me. So basically what we have is root 3 by 2 V sine omega t minus 30 degree. Right? I will remove these calculations. Okay. So this is our V naught. This is our V naught. We will do one thing. We will copy this. We will copy this whole thing and put it somewhere here. This we will need. Right. So see, what we have is this V naught is root 3 by 2 sine omega minus 30 degree. That is, this is lagging VAB by 30 degree. Let it lag. We will look at it later. Now, what is VBC? See, the voltage across this transformer, across this winding is VBC. What is VBC? VBC is omega t minus 120. So, if I draw V small bc, V small bc, that is nothing but N2 by N1, N2 by N1 sine omega t minus 120 degree V. Clear? VBC. Now, and one more thing you see, whatever phase this V naught has, whatever phase this V naught has, let me call this, let me call this V2, instead of VBC, V2, and let me call it V1, okay? Whatever voltage, whatever phase this V naught has, the same phase will this V1 get. And V1 has a phase of minus 30 degree. Sorry, V naught, this is V naught, has a phase of minus 30 degree. So we have magnitude we will write later, omega t minus 30. So you see, if we connect the transformers in this fashion, we are getting two voltages in the secondary which are 90 degree phase apart. Right? V2 is lagging V1 by 90 degree. So one criteria for balanced two-phase supply is fulfilled. We have 90 degree phase shifted voltage. Now, the other part is magnitude. So we have seen that V1 has a magnitude of N2 by N1 V. So V2 must also have a magnitude of N2 by N1 into V. Right? So what we can write is V2 by V naught is equal to our desired voltage in V2 no, not this way, sorry, not V2 by V naught. This number of turns we do not know as of now. So let us take it N naught. So N2 by N0 we are writing as the ratio of number of turns. So N2 by N0 equals V1 by V0. V1 we need this much into, sorry, by V0 we know. So 1 by root 3 by 2 V. V cancels out. So what is N2 cancels out. So N0 becomes root 3 by 2 N1. So as we said that these are two identical transformers, N1 by N2. For this transformer, we used the complete winding of primary with a center tap So N1 by 2, N1 by 2 we got. But for here, we do not need the whole N1. What we need root 3 by 2, that is around 0.8 or something, 0.866 I think, N1. So the whole we do not need. So basically what we need is how the connection would actually look like is, for the primary I am drawing only. One is here with a central tap, with the other with a tap somewhere here. This is not needed. So if this is N1 by 2, this is N1 by 2, this is root 3 by 2 N1. If we do this, then our voltages also match. Secondary voltages also become equal. So then that is also N2 by N1 V sine omega t. So is it clear up to this? Why we need this kind of tapping? Not at the middle point, but somewhere else.
Yes, sir.
Yes, sir.
Now we will look at the currents. For the time being, let me copy this. We will look at the current first. Loads I will remove for now. Okay. So this bold type of connection we have done, removing this. Let us say for the time being that there is no load. Okay. We will only look at the currents. No load currents. There is no load. So this has been connected. So you see what happens is, some current, okay, do we need to look at it for no load? Okay, let's see. So some current, no, let us do it on load itself. There is no point of doing for no load. I am drawing currents with red. So some current, load current it is drawing. I am writing as I1 prime. And that same current reflected obviously is flowing here, I1. And it is also drawing I2. How I2 will reflect here, I will show. But the thing is, I1 is coming down. Where will it go? I1 has to go in some way. So, you see, I1 will see equal impedance in both these windings. So, it will get divided. So, I1, half of I1 will go here. And the other half of I1 will go in this path. Do not confuse with this minus, okay? This is in another color. So half of I1 by 2 goes in this manner, other half goes in this manner. Now you see, we will deviate a bit from here. In the very early classes of transformer, I used to talk a lot about MMF balance. MMF balance. That is, I told you that if you have n number of windings connected wound across the same core, then the total MMF, if they have the same sense of winding, then the total MMF summation over IN has to be 0. In a transformer also the same thing happens. In an ideal transformer there is no core flux. In a practical transformer only the core flux due to the no load current is there, and after that if you connect the load draws the current, the same balancing current flows in the primary, they balance each other, so there is no extra flux. So that MMF balance should happen here also. How is it happening? We will see. You see, I1 is flowing here in this winding, right? And I1 prime is flowing here. So it is such that, okay, I was writing with green. I1 into root 3 by 2 N1 equals I2 N2. This thing holds. This is a simple transformer. You have root 3 by 2 N1 turns in the primary, you have N2 terms in the secondary. This thing holds, you know. What about the, say, other transformer? What apparently looks like is the current that is coming in, some excess current is coming in the transformer. The transformer is supplying some load, but some excess current is coming in. What about it? Will that not disturb the MMF balance? But you see here what is happening. If I draw the primary once again here, the primary is center tapped in this fashion, and we have dots here and here. So some current I is flowing upward, the same amount of current I is flowing downward. See, I1 by 2 is flowing this way, I1 by 2 is flowing the other way. One is going out of the dot, one is coming into the dot. So basically, when the primary current I1 of this transformer comes to the other transformer and gets divided into half, they create two opposite MMF. This I1 by 2 and this I1 by 2, they create two opposite MMF in the core and cancels each other. So this current does not interrupt the MMF balance of the other transformer. Say we will call this transformer as our transformer 1, and we will call this our transformer 2. So the primary current of transformer 1 does not affect the MMF of the transformer 2. And what about transformer 2? Transformer 2 is working naturally. Transformer 2 is working naturally. Naturally means some load is there. Some load is there. This load is drawing some current according to its power factor, I2. And this I2 is getting reflected here in both the windings. So I2 is flowing, like the same current I2 is flowing due to the transformer action, I2, I2. So if I now look at the line currents, how is it? See, no, I drew the I2, polarity is opposite. If the current is coming out here, it should go in here. So this is I2, this is I2. Any doubt about why the polarity is like this? So basically what we have is I2 primed, okay, the reflected ones. I1 by 2, no sorry, we wrote prime in the secondary, so this is primed. This is not prime. This is not prime. I2. So we have I1 by 2 plus I2 flowing here, and I1 by 2 minus I2 here flowing outside. So what we generally draw is we generally give in one way. So if I write it as IA going in, IB going in, and IC going in, I have IA simply as I1. I have IB as minus I1 by 2 plus I2. Sorry, this I wrote as. And these are all vectors, okay? IC is minus I1 by 2 minus I2. Any doubt till now?
Sir, only I have doubt in that equation 1, MMF balancing. Sir, you have written this equation for transformer 1 now? Yes, sir.
Yes, yes.
So in the primary there is I1 into root 3 by 2 N1, but in the secondary there is current I1 dash.
Oh, sorry. I just tried to draw, right. I1 prime. Just the MMF balance of this transformer. Okay. So now if we draw the phasor diagram, how will it look? See, we have our VAB here. VBC is lagging VAB by 90 degree. VBC got longer than VAB. I will make VAB longer. Okay, this is VAB. And VCA is here. Right? Now, what do we had? We have V1 as same with VBC. Just a minute, sorry, this was V2, not V1. This secondary. V1 is this. So, we have this along VBC. The secondary one, V2. This is understandable. VBC is coming across this primary, that is getting reflected, so V2. And the other one was lagging by 30 degree. This is our reference. So, 90 degree to this. This is V1. Same in magnitude, 90 degree, and this is 30 degree. Okay, now we will draw the current waveforms in this problem. Okay, we will solve this problem and then draw the current waveform, current phasors also. So let us do one thing. Let us copy paste this. So we have a diagram here. Okay, we have a diagram here. So you can see the problem, right? Let us read the problem first. It says that Scott connected transformer takes power from a 6.6 kV 3-phase supply, delivers power to two single-phase 100-volt furnaces. Generally, these Scott connected transformers are used for power supplies in furnace, which require a large amount of current, with power factor 0.8 lagging, as shown below. Furnace 1 is consuming 250 kilowatt of power. Furnace 2 is consuming 100 kilo of power. Phase sequence is A, C, B. Okay. So you see, in our case, we assumed a phase sequence of ABC, but this was our B, and this was our C, right? Oh, it hardly matters where is where. Ultimately, you are tapping something in half and connecting one in B, one other in C, so it doesn't matter where you are connecting what. The question is estimate the RMS value of current in IA, IB, IC. Okay, so we will do that. First, we have to find out the ratios of number of turns, right? So we have a 6.6 kV in the primary. So here we have 6600 volt, right? Where here we have 100 volt. It is written that 100 volt, the furnace voltage is 100 volt. So, as our convention N2, N1, we have N2 by N1 equals 100 by 6600. So, 1 by 66. So if this has 100 turns, this has 6600 turns. Now if this has N2, this also has N2, and this has root 3 by 2, N1 number of turns. So let us write, it is not given, can be something else also. Let us write N2 has 100 number of turns. Then N1 will have 6600, and this thing, this primary, this will have 6600 times 0.866, this many of turns will be there. Okay, right. Now, furnace 1 is consuming 250 kilowatt of power. Let me clear this up and draw things once again. I will write the currents now here. So, some current I1 prime is flowing. That current is getting reflected here as I1. Okay. And this current I1 is going out as I1 by 2. So let us write in this direction as minus I1 by 2. And it is going out here. Also minus I1 by 2. No, this is this. Minus I1 by 2. Okay. And this is drawing a current of I2. Actually, in this problem, dots are not given. Without dots, if you ever draw a Scott connection, Scott connected transformers without dots, that actually is meaningless. That does not convey any meaning. You are engineers. If you draw a connection without dots and give it to the people who will be actually connecting things in the field, they will not understand where to connect what. So there should be dots here. Once you give the dots, they know where to, which windings will go where. Okay. So if it is like this, then we have I2 flowing here, I2 prime here, coming out of the dot, so going in of dot, so it is in this direction. This is I2 minus I2. Any doubt about the current directions and the polarities?
No, sir.
Okay. All right. Now we can simply find out the current values. Okay. So I2 prime is something like this. Okay, let us do one thing. Let us first find the voltages. Okay, since we can find out the voltages, let us find out the voltages. So what we have is VAB. Can you tell me what is VAB? What will be its magnitude? Some voltage 6.6 kV is given. What will be its magnitude? VAB is something sine omega t.
90 degrees, sir.
No, magnitude. How much sine omega t? I am taking VAB as my reference.
Okay.
It will be 6.6 k root 3. Sorry, root 2. Line voltage is given. Since I am writing equations in this fashion, I have to write the peak value. So VAB is this. Here the phase sequence is ACB. Okay, let me write VAC then. Otherwise we will get confused. VAC is this. Then VCB will be this minus 120 and ACCB BA. BA will be this times 120, right? Now in our phasor diagram, what did we see? We saw that V1, that is this secondary of the transformer 1, lags the primary voltage by 30 degree. If it is so, we will write V1 here. What will be V1? Can you tell me?
Sir, I want to say something.
Yeah.
So VCB is angles of 0 or minus 120 degree.
Minus 120.
As per derivation, VCB angles is equals to 0.
No, in derivation, what we did is, see, there are two things. The first thing is phase sequence. Here we took a phase sequence of ABC, right? And the second thing is we took VAB as our reference. See here, I will show you the equations. See, we took VAB as our reference. It is sine omega t. Omega t means omega t plus 0 degree. So this was our reference.
Fine.
But in the problem, they have given the phase sequence as ACB, the other phase sequence. That's why I am taking it AC, CB, BA in this fashion. Okay.
Yeah, okay, fine, sir.
So now AC is our reference. Now here, what did we see? Now if do not look at these ABC things because they are different in these two cases. So just look at the entities. We saw that V1, that is the secondary voltage of the first transformer, lags the VAB voltage. VAB is this by 30 degree. Right? So here V1 should lag V AC by 30 degree. Any doubt about it? We're just matching things and writing. Okay? Or else you can do the derivation by yourself also. These things you can take, you can again do the same trigonometric calculations that I did, and you can find this out. Okay? And the magnitude of V1 we know, 100 volt. So we have 100 root 2 sine omega t minus 30 degree, or V1. And V2 will be 100 root 2 sine omega t minus 120 degree. Correct? Now we have fixed our reference. Everything will happen with respect to that. Okay. So now furnace 1 is consuming 250 kilowatt of power at 0.8 power factor. So we have VI cos theta as 250. V is 100. I, see, this is RMS. VI cos theta is power, this is RMS. 0.5 is 250. So what is the RMS value of current that the primary winding is drawing? That will be 250 by 100 times 0.8. A very small amount of power. Oh, it is 250 kilowatt. There, now that's okay, because Scott transformers do not generally supply such low value of current at full load. 250 kilowatt. So into 1000. 3125. So our I1 has a magnitude, so not magnitude, RMS. Let me write RMS of 3125 ampere. And it is lagging, and it has a power factor of 0.8 lagging. So cos inverse 0.8 is around, I will write it in, not make things complicated, 37 degree, let's say. So we have I1. Now can someone tell me what will be the equation of I1, the instantaneous value? RMS we know. Can you tell me the value of I1? Something into sine omega t minus something.
Sir, it is lagging the voltage by 37 degree. So we will write it minus 37 degree.
Lagging which voltage by 37 degree? See, this is a load. So whatever voltage comes across it, it lags that voltage by 30 degree.
That is, it is lagging V1 by 30 degree.
So how much should I write here?
Minus 67.
Minus 67 degree.
Yes.
You see, minus 67 degrees with respect to what? VAC. So basically, this
VAC.
I1 is lagging VAC by 67 degrees. This is our reference.
Of course, sir.
And what will be the magnitude?
By root 2.
Times root 2.
Times root, sorry.
Yeah. So I1 is this much. Both of them are at 0.8 lagging. So we have furnace 2 as 100 kilowatt of power. 100 kilowatt of power at 0.8 lagging. So 1250 as its RMS. So into root 2. Sine, can someone tell me the angle?
Uh, 90 degree further.
90 degree further.
Yes, sir.
So 157. Or we could have told it from here also. Right? This is the voltage across load 2. So 37 degree lagging from here, minus 157. Okay, now we know the individual load currents. We have to find out the primary currents. So what is I1? I1.
I1. Which current?
I1 is this.
It is IA, na, sir? IA.
IA. I1 is IA.
I1 is IA. So it will be the reflection of that I1 dash.
Reflection of this. Oh, I am actually mixing up things now. This is nothing but I1 primed what I wrote here.
Okay, okay. Yes, sir.
First load, second load. So I1 is IA, which is nothing but reflection of this. So it will be
I1 dash by A, that is I1 dash
I1 prime times how much?
N1 by N2.
No, not N1 by N2. N2 by the secondary has a number of turns equal to N2.
Okay, okay.
And the primary has a number of turns equal to root 3 by 2 N1.
Right, sir, right.
Right?
Yes.
So we had N2 by N1 as 1 by 66. So this will be 1 by 66 root 3. 2 will go up. And whatever we have here, 3125 root 2 sine omega t minus 67 degree. Can you please do it and tell me? 2 times 3125 root 2 divided by 66 root 3. Around 77 ampere. Okay, I am writing approximate values. We will quickly do the phasor. That is very interesting. Sine omega t minus 67 degree. Okay, this is I1. Now we can find out I1 or IA. We can find out IB. What is IB from here? Minus I1 by 2 minus I2. So IB is minus this root 2 angle minus 157 degree minus 77 angle minus 67 degree. See, there are two ways to calculate these things. Okay, you have already learned those in your undergraduate classes, means you're all undergraduate, I think, first year basic electrical. So I'm not showing you once again how to do it. I'm quickly doing it in my calculator using complex functions. You can do it with complex functions, or you can yourself find out, split them up in cos theta plus j sin theta and then calculate. Since we have don't have much time. I am doing it in my calculator with something. What is wrong? Okay, just a minute. Okay, it's calculating. It's coming out to be, we will write it in, how to get that it's coming out. Some 1597 plus J 761. Did I do any mistake here? Yes, I did a mistake here. Can someone tell me what mistake I made here in calculating IB?
So you should take the magnitude only then.
No, magnitude only I cannot take. Magnitude only cannot take because these are phasors.
Yes, sir.
What
Angle,
mistake go on?
angle, sir.
No,
Minus
not
one.
angle. No, what I did, mistake that I made is I forgot to reflect them in the primary. These are load, we calculate this from the load power requirement, right? These are secondaries, you see, primes. I forgot to, and now we are doing these calculations, minus I1/2, minus I2, these all are in primary. I forgot to transfer them or reflect them in primary. So this will be times N2 by N1. Isn't it? Minus 77/2. This is I1/2. Angle minus 67 degree. N2 by N1 is 1/66. Okay, can you guys tell me how many of you know how to do complex calculation in calculators? This model of Casio can do it. This is 991 ES. I think you are allowed to use it in college.
Yeah, in college allows to 991 MS Kelsey.
Okay, so 1250 times root 2. If it will be helpful if you can help me to do these calculations faster, because we will be out of time otherwise. I am taking some approximate values, okay? We will focus on the problem. This will come, forgot the minus. Then I will put it's here. You can directly put angle inputs. I am writing 27 angle minus 157 degree. Can you see that I am directly putting angle values here? You can directly put angle values. Minus 38.5 angle minus 67 degree. Take some time. Okay, it has come. Display, where is display? I cannot find it. Complex, I will write it in R theta format. So in R theta format it comes out to be 42 angle 77 degree. Let us keep it like this, okay? Let us not complicate things anymore. And IC is, this is minus, other one is plus. So IC is minus 1250 root 2 angle. If you have doubt, ask me. Times N2 by N1. This will be plus now. See here. Plus I2 minus I1/2. Minus I1/2. Same thing. 77/2. And angle of minus 67 degree. Same thing. The other one just gets plus. Okay, I will see if I can. Okay, I will write it once again. It's 27 angle minus 157 minus 38.5 angle minus 67. Just a second, 27 angle minus 157 minus 38.5 angle minus 67, which comes out to be, okay, some 47 angle 148 degree. This is IC. Okay. Now we will quickly draw the phasor diagrams and then we will call it a day. These equations we need. I could have drawn the phasor diagrams without looking at this, but since these are, did I copy? Since we have some other phase sequence here, ACB, not our regular ABC, I have to look at the equations to draw the, I don't know why it happened like this. Anyway, A, C, B, we took AC as our reference, right? So this is VAC, AC, then VCB. So in your exam or wherever, if you have another phase sequence, do not get afraid, just write the equations or phasors. There will be no chance of making mistake. AC, CB, BA, right? What about V2 and V1? V2, V1 we have seen, right? V2. Okay, I will draw voltage with blue. V2 is somewhere here along VCB, and V1 is here leading V2 by 90 degree. Okay, now you see the loads connected to V1 and V2, they are lagging the voltages by certain angle, by 37 degree. Okay, and V2 load is smaller. So now we will draw currents. So this is the current I2 primed, and I1 prime will lead I2 prime exactly by 90 degree because they have same power factor, although their magnitudes will be different. This is, sorry, not I2 primed, I1 primed, right? Now whatever I1 primed is, reflected to the primary is our IA. Okay. Okay, so let me draw it larger because IA is small. So this is I1 primed. So whatever is this, in phase with it is IA, right? And I2 I will draw larger, not larger than I1. Now we have to draw IB and IC. So IB is minus I1 by 2 minus I2. So if this is I2 primed, I2 is somewhere here along this, not somewhere here, exactly along this I2. So I1 primed minus this will be somewhere here. This is minus I1 by 2 or minus IA by 2, and this is minus I2. So if you do a phasor addition of them, you have your IB somewhere here, and what is IC? I2 will be positive, this will be minus, so just adding them to will give you IC. Okay, so I will tell you one thing, that what you do is draw this phasor diagram Since I drew it approximately there, these angles are not exactly correct. So draw this phasor diagram with proper angle and magnitudes properly scaled. Okay, you do this thing, then you will get a feel of how the currents are getting added, which currents is flowing where, what is their phases, respective positions, everything you will understand. Okay, so that's all about Scott connection. You have any doubt in this whole discussion? Give it a read, okay? This might look complicated because of this thing specially, that this current is getting halved, but their MFs are opposite and the currents are not equal in the phases. But this is easy actually. Just draw this phasor diagram, everything will be clear. Okay, any doubt about it? About Scott connection or anything else? Someone asked about parallel connection doubts. No doubt? Okay, if not, then let's call it a day. We will again meet again on the next Saturday, 7 p.m. And this time we will start with rotating machine. The only rotating machine covered in this course is DC machine. We will see how it looks and why at all we are studying DC machine in 2022. That I will also mention. That's it. Okay, then thank you. Bye. No doubts, right? Okay. All the best. Bye.